Welcome to an introductory lesson on vectors. In this video we will be looking at what vectors are, just how we can sort of graph them. We'll look at how we can express them in component form and also in a form using unit vectors I and j. And then we'll look at how we can compute their magnitude and direction. So first let's define what a vector is. We think of a vector as visually as an arrow or a ray. So it starts at an initial point and it stretches in a direction towards a terminal point. Usually when we write a variable for a vector, we'll either write, like say v for vector, we'll write v with an arrow pointing to the right over it. Or if you see it like typed on a book or on a computer screen, web page or something like that, you might see it as just a normal letter, but bold-faced. Okay, so it can kind of get confusing sometimes depending on the letters you're looking at, because you can confuse normal variables with vector variables. But so just kind of pay attention and keep track of the context of particular problems, and just kind of remember those possible notations. So when we talk about a vector, again, it is an arrow or a ray, but two things we get from having an arrow is its magnitude and its direction. So what we mean by magnitude of a vector really just is how long is it. Okay, so what is the distance from the initial point to the terminal point? So that represents the magnitude. And as far as notation for magnitude of a vector, we write, it looks like just absolute value. So you have your vector variable or your vector expression in between what looks like absolute value signs. Sometimes you may actually see double vertical lines on either side. So that's another way that you might see the magnitude. So it'd be something like this. So a double vertical bar with the V and the arrow, and then another double vertical bar. So those are different ways that you may see the magnitude of a vector represented. And then the other part is the direction. So direction, there's different ways we can talk about direction. It could be, we could express it using its components, which we'll get into all this later. It could also be expressed using an angle. So, is it pointing 40 degrees into the first quadrant or whatever. So there's several options that we have for direction. But whenever we think of a vector, the two things that we always want to think about is magnitude and direction. Now, one specific variable that we want to talk about is the zero vector. So again, the zero vector, what makes it kind of different and special compared to all the other vectors is that we're going to say that the zero vector has zero magnitude. So it's, the initial point and the terminal point are actually at the same point. So there's technically really no arrow, but so we'll say it has zero magnitude and it has no direction. So just kind of a weird one, but hopefully that makes sense. So when we deal with vectors, we like to think about when vectors are equal to each other. Okay, and this is one of the nice things about vectors is that they give us a lot of flexibility. So when are two vectors equal to each other? So for example, say we had two vectors, vector A and vector B, but vector A was a little longer than vector B, but they both point in the same direction. Okay, so in the illustration I have, vector A is a little longer, which means it has a larger magnitude, but vector A and vector B are both parallel to each other. So that means they're pointing in the same direction. In that situation, those two vectors are not equal to each other. We could try another example. Say we had two vectors A and B again. They're actually both the same length this time. The arrows that I drew are both the same length, but unfortunately they don't point in the same direction. They're not parallel to each other. And so we would say those vectors are also not equal to each other. So the third option is that we have two vectors, A and B, that have the same length. So if we drew those arrows out, they'd have the same length, and they are parallel to each other, which means they're pointing in the same direction. So if both of those are if both of those are true, so we have same magnitude and same direction, then we have two vectors that are equal to each other. Okay. One of the weird things about this is you do not have to have the same position for two vectors to be equal to each other. So that means you could have one vector that starts, somewhere in the first quadrant, and you could have another vector that starts somewhere in the second quadrant, but as long as they have the same length and the same direction, so as long as they have the same length and they're parallel to each other, they would be equal to each other. And we'll kind of see how that comes into play here in a moment. So probably one of the most common ways that we express a vector is using its component form. So when we want to think about its component form, let's first just think about what a vector looks like again. It's an arrow. It starts from an initial point, which let's just say that initial point is at the coordinates x1, y1. And the terminal point, let's just say, is at x2, y2. Okay, so we have an arrow going from x1, y1 to x2, y2. If I were to draw out sort of the horizontal and the vertical distances for that arrow, in essence creating a right triangle, that distance horizontally we could call the horizontal component, and the vertical distance we could call the vertical component. So those are when we talk about components, we're talking about horizontal component and the vertical component. And so we can take a vector going from x1, y1 to x2, y2, and we can express it in an equivalent format where we use a notation. So v with a little arrow over it is equal to, and we have these angled brackets. Okay, it almost is like they almost look like a less than and a greater than, but they're not less than and greater than. But so they're not parentheses, so they are actually angled. So we have angled brackets, and the expression, the notation is a comma b. So it looks like it's an x comma y coordinate, but it's actually an a comma b vector because I'm using the angled brackets. Okay, so A and B represent the horizontal and vertical components, and we can then draw that vector AB at the origin. Okay, so if I drew the vector from, and again remember, two vectors are equal to each other if they have the same direction and the same magnitude. So if I could take the vector from x1, y1 stretching to x2, y2, and basically create a copy of it, but starting at the origin, that vector would be the component form vector, and it's equal to my original vector because it's the same length and same magnitude and same direction. But it's helpful to have it starting at the origin. Okay, and so that starting at the origin tells me how far horizontally the vector is stretching, and then how high or how low vertically it's stretching. Now, to find the horizontal and vertical components, to find the horizontal component, you just subtract your x values, x2 minus x1, and to find the vertical components, we're just going to subtract the y coordinates, so y2 minus y1. Another thing that we could look at is how do we compute the magnitude? All right, and so when we compute magnitude, it's helpful for us to have it in that component form. So if we have a vector, vector v, say, and it's written in component form, so that's the angled brackets, a comma b, then the magnitude, which again we write magnitude so it looks like the absolute value of our vector, it is equal to the square root of a squared plus b squared. Now that should sort of make sense if you remember that when we drew the vector, we had a vector and then we had the horizontal distance and the vertical distance. So the horizontal was a and then the vertical was b. Well, C, we call C the hypotenuse of our little right triangle there, then we know a squared plus b squared equals c squared. So if we wanted to find the length of the vector, it's just Pythagorean theorem. Okay. So let's look at an example. So say we have 2 points. We'll just call them points P and point Q. P is at the coordinates -2, 3, and Q is at the coordinates -6, -1. So what we want to do is draw a graph of the vector PQ, and notice how I labeled that. It's P then Q, and the arrow draws from P towards Q. Okay, so that means that P is the initial point and Q is the terminal point. So we want to draw the vector PQ. We then want to figure out its component vector and also draw that on the graph. And then we want to find the magnitude. So let's go ahead and look at drawing our graph here. So we're just going to draw an X and a Y axis. All right, so point P is -2 to the left, and then a +3, so it's up to 3. So point P is at the coordinates -2, 3. Q is at a -6, -1. So 1, 2, 3, 4, 5, 6 in the X direction, and then 1 unit down in the Y direction. So it's down here in the 3rd quadrant. So that is point Q. And again, the arrow points from P towards Q. So when I draw my arrow, my vector, start at point P and draw down to point Q. So that's what my vector looks like. All right, so now let's look at how we can express that vector using a component vector. So again, to do that, the horizontal component is the difference in the X coordinates, and you're always going to do the terminal values minus the initial values. So Q is our terminal point. So A is going to be a -6 minus a -2, which is going to be a -6 plus 2, or a -4. So that means the vector is pointing 4 units to the left. And then we could also do B. That's going to be our Y value. So we're going to do -1 minus 3, which actually also turns out to be a -4. So what this tells me is that PQ, my vector PQ, is equal to a left angled bracket, -4 for the horizontal, comma, -4 for the vertical, and then the right angled bracket. So that's the component form. And again, what that means is that the vector, anywhere, it doesn't matter where you start the vector, but it will go 4 units to the left and 4 units down. Had either of these been positive, it might have been 4 units up or 4 units to the right. So if I wanted to add that vector to the graph, when we do the component form, we start at the origin. So from the origin, I need to go 4 units to the left, so which we already have 1, 2, 3, 4. I also need to go 4 units down. And so our point is right about there. And so we're going to draw our vector here. Okay. Now, if I could draw accurately, our 2 vectors should be parallel. So it looks like they're both pointing down to the left. They look fairly parallel, and they should be in the same length. Okay, and again, they may be a little off here if my drawing skills are lacking a little bit, but they do. It looks like they're pretty much parallel and pretty much pointing in the same direction. So vector V here, it's in component form, starts at the origin and goes down into the 3rd quadrant. All right, and then the last part that we want to look at is how do we find the magnitude of PQ? So the magnitude of vector PQ again, it's equal to the square root of a squared plus b squared. So we know a is a negative 4, so negative 4 squared, plus b, which is a negative 4 squared, and then all of that is underneath the square root. So we're going to have the square root of 16 plus 16, which is the square root of 32. And if we wanted to simplify that, there's 16 is 32 is 16 times 2, and 16 is a perfect square, so we would end up getting 4 root 2 as the magnitude. And if that would make more sense, you could compute it as a decimal, but we do need to be able to compute it as an exact value. All right, unit vectors. Again, this is going to set up another way that we can express what a vector is instead of component form. But a unit vector is a vector whose length or magnitude is 1. So when you compute the square root of the a squared plus b squared, it turns out to be 1. So let's just work through a couple examples here. So let's show that 1/2 comma negative 1/2, that vector, is not a unit vector. So let's compute the magnitude. We want to compute the magnitude of 1/2 comma negative 1/2. And notice when I wrote this, I put the absolute value symbols around the left and the right brackets as well. So it's the magnitude of this vector. It will equal 1/2 squared plus a negative 1/2 squared, all underneath a square root, which 1/2 squared is going to be 1/4. So 1/4 plus another 1/4 will equal the square root of 1/2, and that is definitely not 1. So even though you might think it is because you have 2 halves, and that would make a length of a 1, but when you actually do the magnitude, it does not turn out to be a 1. All right, let's try the other, second one here. So we have the vector negative 3/5 comma 4/5, and we want to do its magnitude again. So we're going to take, it looks like the absolute value, so the magnitude, the vertical line, left bracket of a negative 3/5 comma 4/5, right bracket, and then the second vertical line. So that's our magnitude. We're going to have the square root of a negative 3/5 squared plus a 4/5 squared. 3/5, if you square the 3, you get a 9. If you square the 5, you get a 25. 4/5, if you square the 4, you get 16. And again, the 5 gives you 25. So we have 9/25 plus 16/25, which turns out to be 25/25. And we have the square root of that, which 25/25 is 1. And so the vector negative 3/5 comma 4/5 actually is a unit vector. Okay, it has a magnitude or a length of 1. Now, two specific unit vectors that we have, we refer to as I and J. Some places may actually refer to them like as I hat and J hat. So a hat, if you ever see it, I would write I and put, it looks kind of like an upside down V above it, or we could write J with an upside down V or a caret, so to speak, above it. So that's I hat and J hat. So what these two vectors represent, I is a vector that points 1 unit to the right but 0 units up. Okay, and so when we try to draw this on a graph, so again, let's just quickly look at our x and y axes. The I vector, starting at the origin, points 1 unit to the right. So this is the I vector. Oops. as our I vector. The j vector points 0 units in the x direction, but 1 unit in the y direction. So it's going to point, again, 1 unit up in the y direction. And so that would be our j vector. Okay, so the I and the j vector basically represent the x axis and the y axis. So they're pointing along those are two axes. And so one way that we use these is if another way of expressing a vector is instead of using the component form, so left angle bracket a comma b right angle bracket, we can write a vector as ai plus bj. So to do that, say we had the vector 2, -5. I could rewrite 2, -5 as 2i as a vector. You can also use the arrow 5j. Okay, so again, what does that mean? So if we wanted to graph that 2i minus 5j, that means, and I'm going to try and squeeze it in here, we're going 2 I vectors to the right, and then we're going 5 j vectors, and since it's a negative, but it's 5 units down, so 1, 2, 3, 4, 5. So from the origin, this is our vector. Okay, so it goes 2 units to the right and 5 units down. So that's another way that we can write them. So we have the component form using the angled brackets, or we could write the same vector using the ij format. All right, let's talk about direction. So if we had a vector v, whether it was written in component form or it was written in ij form, so in either direction, a is the horizontal component, b is the vertical component, and we have some direction at which the angle is pointing. So for now, let's think of that angle in standard position. So 0 would be to the right, 90 degrees would be up, and so forth. So just rotating around our unit circle. Again, as far as an illustration, our vector represents the hypotenuse of the right triangle. So our hypotenuse is the length of our hypotenuse is the magnitude of our vector. The horizontal length of our triangle is the horizontal component, and then the vertical length of the triangle is the vertical component, and theta would be the acute angle rotating about the origin. Now, just as an aside here, when we talk about direction, there's a lot of different ways we can talk about it. So you just kind of have to look at the context. Right now, we're defining direction in terms of theta, so it's a standard position angle. Usually, it's going to be in degrees. If you look at more specific applications, maybe navigation or aviation or something like that, they may talk more in terms of degrees north or degrees south or degrees east or degrees west. I think sometimes in aviation they actually say 0 degrees is due north, 90 degrees would be east, 180 degrees would be south, 270 degrees would be west, and then 359 degrees would be almost back up to due north again. So there's different ways that we can talk about it. And you can also think of the direction just in terms of the horizontal and vertical components. Is it going left and right, up and down? So there's different ways we can talk about that direction. But if we think of it in terms of our angle theta, we can come up with the relationship, and this just uses right triangle trig. Given an angle theta, an acute angle theta, rotating around the origin, we know the relationship between the bottom of the triangle, which is the adjacent side, which is A, the horizontal component, and the hypotenuse, which is the magnitude of the vector, has to be related by cosine of that angle. So we could solve that for the horizontal component and get A is equal to the magnitude of the vector times the cosine of theta. if we do the same thing for the vertical dimension, so given an angle theta, the sine of that angle is the opposite over the hypotenuse. So that's going to be b over the magnitude. And if you solve it for b, you get b is equal to the magnitude of your vector v times the sine of theta. And again, similarly, again, right triangle trig, the tangent of your theta is the opposite over the adjacent. So b over a. All right. So we can actually substitute those into our component format, component form notation. So instead of writing AB within the angle brackets, we could say the magnitude of V times the cosine of theta, comma, the magnitude of V times the sine of theta. And we could also express the same thing using I and J notation. All right, to finish up here, let's just look at a couple directions. Let's find the magnitude and the direction of the vector u equals a negative 40 comma 9. Again, the negative 40 comma 9 just represents a horizontal and vertical component. It in essence represents an x and a y coordinate, and so it's not a coordinate, it's a vector, because we're using the angle brackets and the arrow over u. But so we want to find the magnitude and the direction. So again, remember, magnitude, our notation makes it look like an absolute value, and it is equal to the square root of a squared plus b squared. So that's going to be a negative 40 squared plus a 9 squared. 40 squared is going to be 1600 plus 9 squared, which is 81. And so that becomes the square root of 1681. And this is, you might want to use your calculator to simplify this, but that turns out to just be 41. So the magnitude of our vector, negative 40 comma 9, is 41. All right, so that's pretty easy. Let's find the direction now. So you could use the sine or the cosine if you want, but especially since we have the magnitude now, but you have to be a little careful. I want to go ahead and do the tangent, use the tangent equation. So we know the tangent of theta is b over a, and so that means the tangent of theta is going to be 9 over a negative 40. Okay, so 9 over a negative 40 is not a unit circle value. So how do we go about figuring out what that angle is? So hopefully you can remember that we did this using our inverse function. So specifically in this case, we're going to use our inverse tangent. So theta will equal the inverse tangent of 9 over a negative 40. Again, that's something we're going to have to go to our calculator for and just get a decimal approximation. Which, if we do that, we're going to get a negative 12.68 degrees. Okay, that's just rounded to 2 decimals. All right, so is that my answer? And the answer is no. So we have to be careful when we're doing this. Let's think about where the original vector points and where my angle is pointing. So vector u, again, is negative 40 comma 9. So that means it's pointing, if we draw our x and y axes here, it's pointing 40 units to the left and only 9 units up. So it's kind of pointing over here up and left into the second quadrant. Okay. Now remember, tangent, we think about tangent. Tangent is positive in the first and the third. It's negative in the second and the fourth. So when we computed this inverse tangent where is this negative 12.68 degrees? Well, the other thing we think about when thinking about our inverse tangents, inverse tangent, the answer is always going to be between a negative pi over 2 or a negative 90 degrees and a positive pi over 2 or a positive 90 degrees. So the inverse tangent is always going to be in the right half of the unit circle. It's always going to be in the right half. If it's positive, it's going to be in the first quadrant. If it's negative, it's in the fourth quadrant. So that negative 12.68 is actually pointing in the opposite direction. Okay, so it's pointing down here into the fourth quadrant. The problem is my vector is in the second quadrant. So how do we go from the fourth quadrant all the way around to the second quadrant? And we want it to hopefully have a positive value. Well, again, since it's in opposite directions, we know this whole thing is 180 degrees. So if I take 180 degrees and I add it to my inverse tangent answer, we will get the correct angle. And in this case, when we add that together, we're going to get 167.32 degrees. And again, that's just rounded to 2 decimals. So 167.32 degrees is our standard position angle. So that's the angle rotating from the positive x-axis all the way around to where our vector is located at. And another way to do it, if you didn't think to add the 180, is this 12.68 is also equal to the acute angle over here between our vector and the negative x-axis. And then if that's 12.68, we know this is 90 degrees, and so we could figure out what the angle is there. It's a lot easier just to add in the 180, but there's other geometry properties that we could use. So again, for our vector negative 40, 9, we found a magnitude of 41 and a direction of 167.32 degrees. All right, one more example here. Let's say we are given a vector v. We don't know what its components are. We're just told its magnitude is 50 and its direction is given by the angle theta, which is 120 degrees. Let's first find the horizontal and vertical components, and then we'll look at writing in terms of I and j. So to find the components, we know A is the magnitude of the vector times the cosine of theta, and we know B is the magnitude of the vector times the sine of theta. And again, that just comes from the right triangle that we drew, opposite and adjacent and hypotenuse. So A is going to be 50 times the cosine of 120 degrees, and that's going to be 50 times, so 120 degrees is in the second quadrant, and it has a reference angle of 60 degrees. So the cosine of 60 degrees is a half, and since it's in the second quadrant, it's going to be a negative half. And so 50 times the negative half is going to be a negative 25. B is going to be the magnitude, so 50 times the sine of theta, or 120 degrees. So 50 times, so remember our angle is in the second quadrant, so we know sine is positive, so we're going to have a positive answer in the parentheses. So 50 times, and the sine of 120 degrees, or sine of 60 degrees, is going to be a root 3 over 2. And so when you multiply 50 times root 3 over 2, you're going to get just 25 root 3. And again, that's positive. So those are the horizontal and vertical components. And we could write this in component form, but for this example, I just wanted to write it in ij form. So vector v is going to equal a negative 25i plus 25 root 3j. And that would be our vector in ij format.